Hello everyone, welcome to Dream Academy. So this is our control system series lecture number 2. In this lecture we will actually start our actual control system syllabus, because in the first lecture we actually discussed about the basic things which are actually needed to know the control system subject very well, to take the grip in the subject. Okay, so from today's lecture your actual control system syllabus for any competitive examination will start. Okay, so in the previous video, I have said you that I will tell you why the positive feedback system makes the system unstable, why the negative feedback makes the system stable. I will tell you that. So first of all I will discuss that, then I will start the actual video. Okay, so our I am saying that this is a system which has a which is denoting I am denoting as g of s. This is my actual system. Okay, so I am denoting it as g of s, and as this is a automatic control system, so I have a sensor which is taking the output as feedback. I am denoting it as h of s. So this is my actual system, g of s. This is h of s, which is a sensor actually, which is a sensor. Okay, so this is my sensor. Okay, and here a comparator is there inside the system. This is actually the brain of the system. I can say this is a comparator. This is a comparator. Okay, so this is a comparator which is the brain of the system, and this is actually, then this is the output is fed back through the sensor in the input side, and this is my input which is denoting as r of s, and this is my output which is denoting as c of s. This is my brain of the system, comparator. Okay, so let us assume any system. I am assuming that this automatic control system is as a air conditioner, AC. So I am assuming that in this, from this AC I want the output as 25 degrees centigrade, say. Okay, so I want my desired output is 25 degrees centigrade. Okay, so at any instant, let us assume that the AC is giving us 28 degrees centigrade. So I have to control the system so that it will give me the actual output which I actually want. So as this is a automatic control system, because there is a closed loop, I have discussed everything in the previous lecture. So as because this is a automatic control system, so there will be no need of manual changing of the input. It will automatically control the input, so that it will automatically get the output which I actually desired. Okay, so so now for this time, this is my desired, okay, and this is my now actual, okay. So this actual output is sensed by the sensor, and now I am talking about the negative feedback system. Why negative feedback system makes the system stable? Okay, so as this is a negative feedback, so this is feedback through feedback as negative. Okay, so this 28 degrees faded back in this summing block. This is a summing block as negative, so I want 25 degrees centigrade, and here I am getting 28 degree, 28 degree. Okay, 28 degree. So I want 25 degrees centigrade, I get 28 degrees centigrade. So the comparator compares and there is a difference of 25 minus 28, so there is a difference of minus 3 degrees. So the comparator or the brain of the system decides that I have to decrease the output because there is a negative sign. Okay, okay, there is a negative sign. Okay, so it has detected, or it has decided that I have to decrease the output to reach my actual desired value. Okay, so I am assuming that this system has a accuracy level of plus minus 1. That means it can increase or decrease the value, mm, 1 degree centigrade per iteration. Okay, so minus 3 degree it gets, so it have to decrease the value by 3 degrees. So from minus 28 degree it will make the value 27 degree. Again 27 degree reaches here, and the comparator compares, and it decides that I have to, and it compares the value, and now the value is, now this is over. So now the value is 25 minus 27, so this is minus 2 degree. Again the comparator decides that I have to decrease the value, so again it decrease the value from 27 to 26. Why 27 to 26? Why from 27 to not 25? Because it has a accuracy level of plus minus 1 degree centigrade per iteration. Okay, okay, so if this machine has more accuracy level, then it can have a accuracy level of plus minus 0.00001 degree centigrade per iteration. Then the accuracy level of the machine is very high. Here I am just assuming that this machine has a accuracy level of plus minus 1 degree centigrade per iteration. So okay, so again it compares the sensor senses the value 26 degree centigrade, and the comparator compares, and it detects that I have the difference of minus 1 degree centigrade. This is over now. I have the difference of minus 1 degree centigrade now, so I have to again decrease the value. So from minus 20 degree centigrade, 26 degree centigrade to now 25 degree centigrade. Okay, so the sensor senses 25 degree centigrade. Now the difference is 25 minus 25, so this is 0 degree. So now the compare realizes that I don't have to actually decrease the value, because I have reached the value, which I actually desired. Okay, so this is actually working procedure of any negative feedback system. Okay, so I we have seen that in the negative feedback system, the output is reaching at a level, and it is staying at a level which we actually know, which we actually desired. Okay, so now I am talking about the positive feedback system. Again, this is my g of s, which is my system, which is my actual system, and this is my sensor h of s. Okay, I am not denoting again because I have denoted that. This is my comparator, or brain, I can say. This is the summing block which sums up sorry. This is the r of s, this is the c of s output, this is the feedback is fed back to the summing block. This is the summing block which sums up the feedback signal and the actual input signal. Okay, so now this is a positive feedback system. Again I am assuming I am doing it in another color. Okay, So again I am assuming that this is AC. So here I want say output of 25 degrees centigrade, which is my desired value. Okay, which is my desired value. Okay, so again I am assuming that I am getting the actual value as 28 degrees centigrade. This is my value actual value of output. Okay, so this actual value of output is sensed by the sensor, and this is faded back in the input side terminal summing block through a positive feedback loop. So now my desire is 25 degrees centigrade, and my actual value is 28 degrees centigrade. My actual value is 28 degrees centigrade. So now 20, and as this is a positive feedback system, so this is now 25 plus 28, so this will become 53 degrees centigrade again. So the output will be 53 degrees centigrade. So this is now my this is now my this is now my actual output. Again this 53 degrees centigrade will go into the input side through the sensor, and the comparator will sense that, and this will make the output as 25 plus 53. This will become as 78 degrees centigrade. So now this will become 78 degrees centigrade. So as we can see, as we can see that the output is not actually staying or stabilizing at a particular desired value. It is actually keep on increasing in actually in a exponential manner, Okay, so this is not a nature of a stable system. So from this we can say that the positive feedback system makes our system unstable, and the negative feedback system makes our system stable, because in this case we can say that our output is reaching at a particular value or desired value which we want after some iteration. But in case of positive feedback system, the output keeps on increasing in a exponential manner. Okay, so now we will come to our next topic, which is our our actual start of control system subject. So our first topic of our control system subject is transfer function and impulse response. Let me do one thing. Let me write the whole syllabus for your control system. This is your 1. Now 2 is transient analysis. Now, or we can say this is as time domain analysis. Then my stability analysis. Under this there is two subtopic. One is RH criteria, another is root locus. Okay, now the fourth is frequency response analysis. Frequency response analysis. Under this there is three actually polar three plot. First of all is polar plot, second is Nyquist plot or Nyquist plot, and third is Bode plot. Okay, and the fifth topic is controller and compensator. Controller and compensator. And the sixth and the last topic is our modern control theorem. Or the state space analysis. Okay, so these six are the topic which we have to cover for any competitive exam for your control system subject. Okay, so now today we will start the first topic, which is transfer function and the impulse response. Okay, so first of all, let me tell you what is actually transfer function. Transfer function means what is the output, with respect to my input. Okay, what is my output with respect to my input? That is actually my transfer function. Okay, so let us assume a closed loop system. This is my G of S main system, then this is my H of S, which is my feedback loop gain or the sensor. This is the summing block, and this is faded back, this is negative feedback. Okay, so this is my input, this is my output. Okay, this is my output. Okay, so I'm assuming that this is A, which is coming here, and the signal which is going in the forward path, I am saying this is as B. Okay, so I have to find the output with respect to as a function of R of S. Okay, R of S, and the forward path gain G of S, and the feedback path gain H of S, and the function which is C of S by R of S is actually my transfer function. Okay, is actually my transfer function. Okay, so here the A is what? C of S into H of S. So A is C of S into H of S. What is my B? B is equal to R of S minus A, because here is a minus, negative feedback. So R of S minus B minus A. Okay, and my A is what? And my A is C of S into H of S. C of S into H of S. Okay, so now what is my C of S? My C of S is equal to B into G of S. B into G of S. Here this is B and this is G of S. So total C of S is B into G of S. So b, now I am putting all the values. B is equal to R of s minus C of s into H of s, and this total is multiplied by G of s. This total is multiplied by G of s. Okay, so I can spread the whole thing, R of s into G of s minus C of s into H of s into G of s. Okay, and this is my C of s. This is C of s. Okay, so now C of s I can take it in this side and take common, so 1 plus G of s H of s, G of s H of s, and here in this side R of s into G of s. So I can take the R of s this side, so C of s by R of s, and this I can take, and this I can take in this side, this I can take in this side, so this is G of s by 1 plus G of s H of s. So this is my C of s by R of s. So this is actually what? This is my transfer function, and the transfer function with with respect to or in the terms of G of s H of s. Okay, so this is my transfer function, and transfer function is in terms of G of s H of s. G of s is my forward path gain, H of s is my feedback path gain. Okay, so this is my closed loop transfer function. So my CLTF of any control system, or my CLTF closed loop transfer function of any control system or any system is G of s by 1 plus GS HS. Here G of s is the forward path gain, and H of s is the feedback path gain. Okay, so now this is my transfer function. This is my transfer function C of s by R of s. I can denote this transfer function as H of s. Don't think that this H of s is the feedback path gain. This H of s is the denote of is the notation of the transfer function. This is the terminology actually of my transfer function. Okay, this is not feedback path gain. This is different. This is different. This is my notation for transfer function I am using. Okay, so if I take this out this side, so C of s is equal to H of s into R of s. So if I inverse Laplace this, so C of t is equal to H of t into R of t. This R of t is input, this is my transfer function, this is output. So so if I take this input as my impulse function, so C of t is equal to H of t into del of t. So we know that my now again if I use Laplace transform, this will become H of s into 1. Okay, so as we know that the Laplace of the impulse function is 1, so this will become C of s is equal to H of s into 1 after doing the Laplace transform. So we can say that inverse of the inverse of the Laplace transform, or the inverse Laplace of the transfer function, is the impulse response. So my impulse response is what? My impulse response is here C of s. My C of s is the impulse response because I have given the impulse as the input, So c of t in the time domain or c of s in the Laplace domain is now my impulse response. Okay, so if I again inverse, I again do inverse Laplace of this of this impulse response, I will get, I will, so if I do inverse Laplace of this impulse response c of s, I will get c of t is equal to what I will get, I will get h of t. So I can say that, here del of t I will get, so I can say that the inverse Laplace of the transfer function is the is the impulse response. Okay, is the impulse response is this, and this is c of s is equal to h of s is into 1 is equal to my what is equal to my is equal to my inverse Laplace is equal to my transfer function, this c of s is equal to h of s. So if I do the inverse Laplace of this, I will get the impulse response of the system. Okay, so one point you have to note, that is the inverse Laplace of the transfer function is the impulse response of the system. Okay, so why this is, because when I am giving my input as delta in my system or impulse in my system, then I am getting the output as c of t is equal to h of t into del of t. Okay, so after doing the Laplace, I am getting as c of s is equal to h of s into 1, because this is del of t, is Laplace transform is 1. So this is my transfer function, because h of s is my transfer function. So h of s is equal to c of s is my transfer function. So after, now if I do inverse Laplace transform of this, I am getting c of t is equal to h of t into del of t, or I can say that there is a convolution, because in time domain, there is the signal multiplication is known as convolution. Okay, so this is the thing. From this particular concept you will get question in any competitive exam surely. Okay, so this is over now for closed loop control system. Now I will talk about the open loop transfer function or open loop system, open loop transfer function of any closed loop system. What this actually means? This actually means I have the system g of s, I have the feedback path gain h of s, I have the input r of s, I have the output c of s, and this feedback is actually not connected. Okay, and this feedback is actually not connected, this r of is here actually. Okay, and this feedback is not connected, feedback path is here, but feedback is not connected. In this case, my open loop transfer function will be g of s into h of s. Okay, how this is coming, this is not important. you are just studying for the competitive exam, so you have to just know that the open loop transfer function is the g of s into h of s. G of s is your forward path gain, and the h of s is the feedback path gain. Okay, so this is my open loop transfer function. So we can make a table, that CLTF, closed loop transfer function, and OLTF, open loop transfer function. Here I can make a table, and here this can be the transfer function. Here feedback connect or not, feedback connected or not. So the transfer function of CLTF is g of s into 1 plus gs hs. Okay, here this is g of s, h of s. Here feedback is present and connected. Here present but not connected. Okay, so both are actually closed loop system, but why we are telling this as open loop transfer function of closed loop system? Because here the feedback path is there, but that is not connected, so we have made the closed loop system as open loop. Okay, and we are seeing what is the transfer function, so this is we are calling as open loop transfer function for a closed loop system. Okay, so today's lecture is only about up to this. From the after this video, that means in the next video I will start the methods by which you can actually tell the transfer function of any system by looking at the block diagram of that system, mm, or the circuit of the system. You can say what is the transfer function of that system. That methods, there is two method, one is block diagram reduction method and another is signal flow graph method. From that thing I will start my next video or the next um, teaching session. Okay, so for the next video I am giving you some homework. You have to do that, because if you don't do that you will not do good in the control system. Okay, so I am just giving you two problem of Laplace transform. You have to just find the inverse Laplace of that functions. Okay, so just try that in your home. If you don't mm, if you can't do, then I will solve that, but just try in your home. This will help you a lot. If you can't do that, just after trying, if you can't do that, I am here, I will do that, but just try it. Try in your home. Okay, just try in your home. So I can say this is homework 1 is function of s is equal to s plus 4 s square plus 2s plus 4. This is one, and another is s square, a function of s is equal to s square plus 2s plus 3 s square plus 3s plus 6. These two problems you just try in your home. If you can't do that, that is okay, but just try in your home. don't leave it alone, just try in your home. That will help you a lot. Believe me, that you help me a lot, help you a lot, help me a lot, because if you know this Laplace transform, inverse Laplace transform, you will understand the subject very well. Okay, so you just have to try this in your home. If you can't do, I will solve this in the next video. Okay, so till then, take care, goodbye. If you like our series, just subscribe our channel, share with your friends, like our videos. Goodbye.